Alright, time for another draftphysics.com, debatephysics.com also. But again, as stated, tough to find somebody who actually will debate the physics subjects. And there are subjects, there's experiments that need to be debated in terms of what they really say. You know, how they can be rationally interpreted. And it really shouldn't be that complicated. But anyway, it apparently is. Uh, so, it's just going to be a continuing saga, I guess. It's going to take forever to get this job done. Because human beings suck. They're just such lying sacks of shit. So, I'll just move this stuff around while I'm sitting here. Anyway, okay. New stuff. Alright, so I had a really good thinking day. So I guess the debate was good for something because it got me thinking, and it was all quite productive. So I guess the first thing I'll do is just a quick update on helium nucleuses and what I'm pretty sure the model is now. So these will be the electrons. And it's three-dimensional, so you can't. I mean, it's just such an obvious way to arrange them. I should have thought of it before. So the idea would be two would be in these locations, and then you would have the one behind and the one forward here. Right? I think that's the way to draw it. So there's the four hydrogens. And really, I should put it over here, I guess. Anyway, so the electrons would be definitely repelling each other, but they're really attracted because there's four protons. So the four protons are obviously going to attract, to each one of the electrons very strongly on either side of that. Those four protons, and the protons will repel each other, but again, they're going to be very attracted to the two electrons, and so it would basically be a flexible thing, a thing that would, as the electrons move in, the protons would move in. So the whole thing is collapsible and can grow and shrink in size, and that probably has something to do with how it moves, okay, and continues to move. But it's very tight in terms of it's not something you can know why helium is very inert is because nothing's going to really want to connect to this electron with four protons surrounding it. And obviously likewise for the other one. So it makes for a very tight nucleus, and then you would add electrons out here somewhere in the other two dimensions of space, and that would complete the actual molecule or atom of helium. So yes, the two neutrons really aren't neutrons when it's in an atom, and the idea would be as if you were to knock this out. Let's say you hit this with a gamma ray, this electron, it would plow into this other one, push on it, and both of them would leave, and that, I would argue, is a muon. Fits the profile of a muon. So that's how muons are created. And also, if you were to knock one of these electrons out, it's likely it would take one of the protons with it, and that would become the neutron. So if the electrons were knocked out of the nucleus, it's pretty obvious, in my opinion, that yes, they would likely be going right next to a proton as they're leaving and take it with them. So it all fits in a lot of ways, so I like it. Alright, the other subject starts with, probably going to need my notebook eventually here, kind of a lot of stuff to go through. Sorry. I guess I should pause. That's the right page there. Okay. Yeah, I'll be back. Alright, so the first it starts with, is that working? Yes, it is. So this argument about how gravity works, okay, So the argument I have been making, okay, and somebody I talked to in that debate, one of them said, "Oh yeah, we all believe that gravity causes the heat inside of planets." And it's kind of funny if they're going to admit that, because that sort of is, obviously by their theory, free energy, because there's no mechanism to restore it back into gravity, a bent geodesic. So all of this matter that's in space gets pulled into one of these gravitational bodies, and it provides pressure. Okay, it causes pressure, all right, to build up inside, and it melts the core of all of the bigger objects. Now, the small objects are also getting hot, but obviously they don't get as hot because they're not collecting as much pressure per second, because they don't have enough mass, to be compressing, it's how much mass is on top of you will decide how hot you're going to get. All right, and so it fits really well. So this is under high pressure, lots of force ends up in the core of any gravitational body. So the argument is by their theory, some magical bent geodesic gave things physical momentum that clearly turned into heat, and then we know the object's going to be at a kind of equilibrium. The fact is that it's delayed, but it's still equilibrium. So the same amount goes in as comes out. It's just that the force in is way ahead of the force out. One step ahead, let's just argue. And therefore, it still creates a differential in the net amount of force you're getting hit with from above versus the force coming up from below, because it's one unit of force behind, because it's trapped making heat in the earth. So the force goes in, it's slowed down, it doesn't pop back out when it should, and therefore you're in a deficit that causes gravity. So anyway, but what's going to happen is all of that heat has to eventually radiate out. So none of it disappears, it all radiates back out, and it's exactly the same amount of energy that went in. So the same energy that created this heat radiates out. Now the force that created it is this bent geodesic that they say isn't a real force, right? I should show the image actually instead of having my head on top of it. Sorry, I'm a bit tired, but I did want to make this video anyway. Long day and such, long night. So bent geodesic creates heat. The heat goes into the universe. Now right there we know we have a thermodynamic conservation problem, because I can't turn this heat back into a bent geodesic. I can't turn it back into bent space. There's no mechanism to turn these photons, this EM radiation, into wherever bent space is. Okay, so that ain't going to happen. And so the simple argument is all the other suns are doing exactly the same thing. And when you add all of that up, all the other planets, all the other pieces of mass in the universe are also radiating energy. So it's all conserved in that sense. And obviously we're getting bombarded by a ton of radiation. That would be the cosmic background radiation. And plus some portion of that radiation, I would argue, that doesn't have a frequency, okay, because it's bounced back and forth by numerous suns. It's been bouncing around in the universe, and its frequency has been degrading with all of the scatter that takes place, traveling through all of that space and hitting hydrogen atoms, and its frequency just keeps getting degraded, and it finally hits the earth as microwave radiation rather than regular radiation. Okay, higher frequency radiation. And the reason why there's a cutoff at microwaves is the really interesting part. So that's what I will try to explain now. But you can see the system works perfect if I just assume, well, the radiation hits the earth, causes the pressure releases the same amount of radiation in the end. Okay, if we turned off gravity right now, the heat would dissipate out of the Earth back into space, so there would be a net nothing, no difference. It would be as if nothing consumed it, and so therefore it would still be in space pushing on everything. So, you know, it's you can't get rid of it. So anyway, that's the conservation, though. It's just, it's the same force. Okay, the same force pushes in on the planet, creates the heat radiates out again, and it just recycles, and all of the mass is just doing that simple process, and it's all under the same gravitational constant. Alright, so the more interesting bit is what I will call the three phases, okay, of photon creation, or EM radiation, the three ways it can manifest. Alright, so number one would be radio frequencies. And so what's happening with a radio frequency is you have a row of atoms, alright, and you're going to send a pulsed signal into the array of atoms. So you're sending a pulsed frequency, and what you're basically doing is just sitting there and saying, okay, the electricity goes up the antenna, it fires this atom first, so this one has a head start on all the others, and basically a little sequence of photons, something like that. Now I should draw this to scale, okay, so, but I'll do it just for this, just, okay, you're going to have to really, you know, pay some attention to understand this point. But anyway, alright, so that's your frequency. Every time you shot the electricity up the atoms, it pulses the atoms as the electricity goes at the speed of light through the atoms, and it creates this signal. So that's the radio signal. So it's just a bunch of elements of a photon hitting a surface. Now, these would be photons. Each one of these little pulses here, this little, say, three things here, this would be a photon. The catch is, though, is they're too far apart, okay, because the atoms themselves are too far apart. So you can sort of see if these atoms were big atoms, or the electrons were far from each other, or there was a lot of electrons, okay. Every time it hits an electron, the electricity is slowed down a little bit, because the electron moves slower, okay, than the speed of light, obviously, the speed of the force. So the electron consumes some of the speed of electricity. That's why electricity doesn't move at the speed of light in these kind of conductors. And so what's happening is the atoms of a conductor are big atoms, or you could argue they have a lot of electrons. So the electricity hits a lot of electrons, has to move a lot of electrons. And but the fact is that the spacing between the atoms is too big. So the atoms themselves are big, which means that the distance between each one of these photon elements moving in space, the distance between them, this way, their polarization, ends up being too big. Alright, so they're separated by too much distance to land on a surface and be received as a photon. So the individual things here that would be a photon are too far apart up and down to be received as a visible photon. And it's not unless you push, like say you have a conductor and you push the electricity in hard, that is too much electricity, high pressure, high wattage. That high pressure basically heats, which is pressure, so it's compressing the atoms. So it takes these atoms and compresses them, okay, into a smaller condition, squishes them, however you want to describe it, and now they're closer together. So you can understand if I squish this row, make all these, well, I should draw it this way, let's say. I make them fatter. You can understand that now the distance is shorter, okay, between them. And so now when they pulse, the photon, the first bit leaves, and then this one leaves closer, and this one's closer. It's closer to each other. So now that can be received as a photon, because when it hits a surface, it's going to have the right length of polarization. All right, so then it'll be a photon. So a photon is made out of just one of these hunks moving through space, and a visible light photon. And the radio wave is this. So those are the transition, and that happens at microwaves. So the key point where you go from this being the signal, the frequency, to this being the frequency. You know, the distance between here and here. All right. So for radio waves, it's the distance for this, that's the frequency. And for the photon, it's the distance, you know, let me draw it more exaggerated. Okay, so for visible light type photons, this is the frequency. The distance between this distance ends up being the frequency, and the polarization is narrow enough, okay, the difference in their height of their difference as they're traveling parallel, for them to be a visible photon. And so that's I don't know what to call it yet. I haven't figured out what the word would be. I mean, it's a phase change. It's a different kind of photon. So that's the second kind of photon. So there's two kinds. There's radio waves, okay, that are this whole giant clump of photons at a frequency created by a pulse of electricity. And then there's the little bits of electricity, the part that's creating the little bits. And the little bits, if the atoms are close to each other enough, okay, then the polarization is narrow enough, and then the surface can interpret the frequency between each discrete little bit. So instead of the difference between the clumps being the frequency, the difference between the distance between the bits becomes the frequency. And so that's like at the transition of infrared light. So infrared light would be this, microwaves and radio would be this. Alright, so that would explain why there's a peak at microwaves and then it stops, is because you can't transition from this form of electromagnetic radiation to this form of electromagnetic radiation. Then there's the third phase, okay, which takes you to the ultraviolet catastrophe. So, and that's based on the fact that you can't find a substance, okay, where the atoms are close enough to each other to create the very small frequency of the ultraviolet frequency. So you can't, it's hard to make ultraviolet light and X-rays because you can't find atoms that are close enough to each other, so when the electricity goes through those atoms, the pulse, that those atoms produce the next bit quickly enough, all right, to keep this frequency tight. So the frequency can't get any tighter than this using common substances. Sorry. So, that one you missed too. You can't do it with common substances. You can't make this tight frequency. So that's where you have to resort to hitting some substance with an electron, like tungsten, I think they use. So they shoot electrons at different materials, one of them being tungsten, and the X-rays, okay, are created by the tungsten because you're basically degrading, you're breaking the atoms, and when you break the atoms, then you're able to create the higher frequencies, but you can't do it just with electricity. So I think that's going to be fruitful in the future in terms of understanding why there are these transitions and why the cosmic background radiation stops at this infrared threshold. I'll have to see what the exact frequency profile is for the CMB, and that'll tell a lot about where the border is. So if anything goes across that border, like a photon gets that little bit further apart between the little bits flying through space, they get a little bit too far apart, that won't be seen as either photon. It won't be seen as radio, and it won't be seen as a visible light type photon. So it'll just be kind of chaos photon. It'll go back to being, I don't want to use the word chaos, but unformed. It'll lack a pattern, and therefore it can't be received by any substance because there's no pattern, there's no signal in it essentially. And so that's the nature of gravity. So there's a whole bunch of the CMB that we don't see, even with our instruments, because you can't see it because it doesn't have a radio frequency, and it doesn't have a photon, visible photon type frequency, that is from infrared to ultraviolet. It doesn't, or short of, from infrared to blue, it doesn't have one of those visible frequencies, and it's not a radio signal either. So if it's not one or the other, you're not going to see it. So I think that's, well, I'll go check my notes. I think that's the gist of it. I don't know if I did justice to it, but it's what you get. Alright, so summing up. Alright, so the energy manifestation of gravity is heat. And the heat always gets radiated back, so there's absolutely no need for bent space. I can just erase bent space. And it's just logical to understand that the consequence of gravity is a tremendous amount of heat. The heat has to leave, and it does. And that heat, those photons, end up recreating the gravity. It's just that simple, that's circular. It's just a simple form of a heat engine, in the sense that you have heat in the core heat radiates out, the radiation pushes on the object, creating the core heat. And it's just a cycle, an engine, just keeps running and running and running. And of course the helium nucleus. So we'll have to see what their diagram of a helium nucleus is. But yeah, I think this is the winner. And the cycles of the phases that photons can be in, the three phases of their evolution, you could argue. The radio waves are pulsed electrical signals. The photons are created by just the atoms, each individual atom being fired by the electricity as it goes through the wire or conductor. And what decides whether it's going to be a visible photon or not is how close the atoms are. If the atoms are too big, no photon. It can't be received on the surface because the pulses hit too far apart. And so if they're smashed together because of heat in the conductor, and you make the atoms smaller, then the polarization is smaller, and now it's a visible photon. So that's why you have to heat things to create visible photons. Now the argument would be is you're creating lots of photons when the wire isn't burning, but and again, you're not really creating the photons, you're jiggling the electrons, and the electrons are pushing on the external force and compressing it. So I should have made that clear, that all of these things don't come out of the wire. The point is the electrons push out, and now the reflections happen sooner than they would. It compresses everything that's hitting. So if a frequency comes in, it compresses it by moving forward. It stretches it by moving backwards. So every time the electron moves, it's compressing and then stretching the signals that are coming into it. So I don't want to make any confusion here. The screwing around with the atoms doesn't excrete more force. It just changes the surface's jiggle, and the jiggling on the surface is bouncing the things that are bouncing into the surface and throwing them back at a new frequency. And that's obviously creating the magnetism, which is going to be a symptom of you changing the pattern of this electron motion. All right. And yeah, so that's probably enough. Okay, so till the next time, and such and so forth and whatnot.